and scattered microscopic dust grains. This, then, is what fills the space between stars, not nothing, not the featureless void of popular imagination. It is a dynamic, layered, magnetically threaded, radiation-saturated, chemically active medium with temperature extremes spanning 5 orders of magnitude, density variations covering 4 orders of magnitude, solid particles catalyzing molecular formation on their microscopic surfaces, and high-energy particles streaming through every cubic centimetre at nearly the speed of light. It has physics, it has chemistry, it has structure at scales ranging from the submicrometer dimensions of individual dust grains to the 100-parsec spans of supernova-carved superbubbles. It is a subject that fills journals and sustains entire research careers. Telescopes across the electromagnetic spectrum, from radio dishes to gamma-ray observatories, are devoted to studying its properties. And none of this changes the fundamental practical reality. 1 atom per cubic centimetre is not a resource. It is the ghost of a resource. A magnetic field of a few microgauss threading through light years of vacuum is not a shield. It is a structural feature of the void itself. Dust grains separated by distances larger than concert halls are not raw material. They are isolated motes adrift in a desert that makes the Sahara look like an ocean. Cosmic rays arriving from every direction at every moment are not an inconvenience. They are an unceasing assault with no shelter anywhere in the medium capable of stopping them. The interstellar medium is one of the great paradoxes of physical science. It is simultaneously fascinating and useless, rich in phenomena and devoid of anything an organism or a machine could exploit. It is an ocean with no water you could drink, a landscape with no ground you could stand on, a sky with no air you could breathe. It is there. It is real. It has been studied for a century and will be studied for centuries more. But for anything attempting to cross it, to survive within it, to use it as a medium of travel rather than a subject of remote observation, the interstellar medium offers precisely nothing. Its phases and structures and magnetic fields and molecular species are irrelevant to the traveller. What matters is the absence of usable matter, the absence of harvestable energy, the absence of shielding, the absence of landmarks, way stations, or any feature that could serve as a resource rather than a hazard. The interstellar medium is not empty in the way a layperson imagines, but it is barren in a way that is, if anything, worse than true emptiness. Because true emptiness would at least be simple. The interstellar medium is complex, structured, and actively hostile, a thin stew of radiation and magnetism and near vacuum that extends for light years in every direction without offering a single handhold to anything passing through. What this barrenness means, when combined with the staggering distances that separate one stellar system from the next, is a question that transforms the interstellar medium from a scientific curiosity into something far more consequential, a barrier so vast and so featureless that crossing it challenges the limits of physics itself. Knowing the composition of interstellar space and understanding what it means to exist within it are two fundamentally different things. Everything described so far about the interstellar medium has been the language of a physicist, cataloguing phases, measuring densities, tracing magnetic architecture. All of that is accurate. All of it matters scientifically. But none of it answers the question that actually haunts the human imagination when we look up at the night sky and wonder about the stars. Could we ever get there? Could anything get there? And if not, why not? The answer is not a simple no. It is something worse than no. It is a cascading series of physical constraints, each one independently daunting, that combine to produce a barrier so comprehensive that it challenges the limits of what any technology, no matter how advanced, could plausibly overcome. Interstellar space does not block travel with a wall. It blocks travel with distance, deprivation, and time, the 3 most patient adversaries in all of physics. Begin with what happens to anything that leaves the heliosphere and attempts to persist in the interstellar medium without the protection of a star. Inside the solar system, energy is abundant. Sunlight floods the inner planets with a generous and reliable power source. At Earth's orbital distance, the solar flux delivers approximately 1,360 watts per square meter. A surface the size of a dining table, aimed directly at the sun, receives enough energy to power a small home. Even at Jupiter, 5 times farther from the sun, solar panels can still generate meaningful electricity. The Juno spacecraft operates entirely on solar power at Jovian distances, a testament to how far solar engineering has advanced. But solar intensity obeys the inverse square law. Double your distance from the Sun and the flux drops to 1/4. Triple the distance and it falls to 1/9. By the orbit of Neptune, roughly 30 astronomical units from the Sun, solar flux has diminished to approximately 1/900th of its value at Earth. Still technically usable with very large arrays, but marginal. By the heliopause at 120 astronomical units, the flux has fallen to less than 1/14,000th of what Earth receives. And these are still distances measured within the heliosphere, still cosmically trivial compared to the gaps between stars. At 1 light-year from the Sun, the solar flux has diminished to roughly 1/4 billionth of its value at Earth, amounting to a few 10 millionths of a watt per square metre. To generate even a single watt of electricity from sunlight at this distance, even with optimistic panel efficiency, you would need a solar array with a collection area exceeding tens of millions of square metres, an expanse rivaling the footprint of a major international airport, just to power a single light bulb. At the distance of the nearest star, over 4 light-years away, the Sun would appear as nothing more than a moderately bright star in an unfamiliar sky. Its energy contribution to any spacecraft in the vicinity would be indistinguishable from zero. This creates a problem that has no analogue in the history of human exploration. Every previous journey undertaken by our species has occurred within an environment that offered at least some possibility of sustaining the traveller along the way. Ocean voyagers could fish. Arctic explorers could hunt seals. Even astronauts in low Earth orbit receive abundant solar energy and can be resupplied from the surface within hours. The fundamental assumption underlying every expedition in human history is that the environment through which you travel, however hostile, contains something you can use. Food, water, energy, raw materials, shelter, something. Interstellar space contains nothing you can use. The solar wind that powered your departure has ceased. The sunlight that energized your instruments has faded to irrelevance. The interstellar medium surrounding you, 1 atom per cubic centimetre of thin hydrogen gas, cannot be collected in useful quantities, cannot be burned, cannot be fused without infrastructure so massive it defeats the purpose. You are moving through a region that is not merely inhospitable, it is inert. It offers precisely zero assistance to anything passing through it. This means that any vehicle travelling through interstellar space must carry its own energy supply from departure to arrival. There is no recharging. There is no topping off. Whatever energy the spacecraft carries when it leaves the solar system is all it will ever have, minus whatever it loses to inefficiency and entropy along the way. Current spacecraft use radioisotope thermoelectric generators for deep space missions. These devices convert the heat from radioactive decay of plutonium-238 into electricity. They are reliable, long-lived, and independent of sunlight, but they are not eternal. The plutonium decays, the thermoelectric materials degrade. Output drops by roughly 4 watts per year for the generators aboard the Voyager spacecraft. Within decades, the output becomes insufficient to power even basic instruments. Within a century, the generator is functionally dead. Nuclear fission reactors offer more power for longer durations, and designs for space-rated fission systems have existed since the 1960s. The Soviet Union flew over 30 fission-powered spacecraft during the Cold War, and NASA has periodically revisited reactor concepts for deep space applications, but even fission fuel is finite. A reactor sized for a modestly powered spacecraft might operate for decades, perhaps a century with careful fuel management. It cannot operate for millennia, and the distances between stars demand millennia of travel time at any speed currently achievable by human engineering. The energy deficit extends beyond mere electrical power. Propulsion itself requires energy, and the energy requirements for interstellar travel are not merely large. They are functionally absurd by current technological standards. Consider the most basic version of the problem. The nearest star system to our Sun is Alpha Centauri, located approximately 4.24 light-years away. 1 light-year equals roughly 5.88 trillion miles. The total distance to Alpha Centauri is therefore approximately 25 trillion miles. Voyager 1, the fastest human-made object on an outward trajectory from the Sun, travels at roughly 17 kilometers per second, or about 38,000 miles per hour. At this speed, the journey to Alpha Centauri would require approximately 73,000 years. 73,000 years. When that journey would have begun, anatomically modern humans were painting on cave walls in Europe and sharing the continent with Neanderthals. Every civilization that has ever risen and fallen on Earth, every empire, every religion, every scientific revolution, every war, every work of art, fits comfortably within that travel time with room to spare. The entire recorded history of humanity, roughly 5,000 years, represents less than 7% of a single trip to the nearest star at our current best speed. What about faster? The Parker Solar Probe, during its closest approaches to the Sun, reaches speeds of approximately 192 kilometers per second, making it the fastest human-made object ever relative to the Sun. If a spacecraft could somehow maintain that extraordinary velocity on an outward interstellar trajectory, the trip to Alpha Centauri would still take approximately 6,600 years. The ancient Sumerians were inventing cuneiform writing roughly that long ago. An entire arc of human civilization would pass before the spacecraft arrived. To bring the travel time down to anything remotely approaching a human lifetime requires velocities that are, by current engineering standards, almost inconceivably fast. At 10% of the speed of light, roughly 30,000 kilometers per second, the crossing to Alpha Centauri would take approximately 42 years. A crew departing in their 20s might arrive in their 60s. Demanding, but not impossible in principle for a single generation. At 20% of the speed of light, the trip shrinks to roughly 21 years. Almost manageable if everything else about the mission could be solved. But achieving these speeds requires energy inputs that dwarf anything humanity has ever produced for a single purpose. The kinetic energy of a moving object scales with the square of its velocity. Double the speed and you quadruple the required energy. To accelerate a modest 1,000 kilogram payload, roughly the mass of a small car, to 10% of the speed of light requires approximately 4.5 times 10 to the 17 joules of kinetic energy. This is equivalent to roughly 107 megatons of TNT, more than twice the yield of the most powerful nuclear weapon ever detonated, the Soviet Tsar bomber, and that calculation accounts only for the payload itself. It ignores the mass of the propulsion system, the fuel, the shielding, the life support systems, and the structural framework required to hold everything together. It also ignores the energy needed to decelerate at the destination, which for a conventional rocket doubles the total fuel requirement through the tyranny of the rocket equation. For a crewed vessel with enough mass to sustain human life for decades, the energy requirements escalate by orders of magnitude. A ship massing 100,000 kilograms, modest by the standards of any crewed vessel that could plausibly support a crew for 40 years, would need kinetic energy equivalent to tens of thousands of megatons of TNT to reach 10% of light speed. The total energy output of human civilization in an entire year is roughly 5.8 times 10 to the 20 joules. Accelerating a single, modestly sized starship to a useful interstellar velocity would consume a significant fraction of global annual energy production, concentrated into a single act of propulsion. These figures assume perfect efficiency, which no real propulsion system achieves. Chemical rockets, the workhorses of current spaceflight, have exhaust velocities of a few kilometers per second, hopelessly inadequate for interstellar speeds. Ion drives, which use electrically accelerated plasma, achieve higher exhaust velocities but produce minuscule thrust, requiring decades of continuous operation to build up even modest velocities. Nuclear thermal rockets improve on chemical performance but still fall far short of what interstellar distances demand. Nuclear pulse propulsion, the concept of detonating nuclear bombs behind a spacecraft and riding the blast waves, could theoretically reach a few percent of light speed, but requires thousands of nuclear detonations and raises engineering challenges that have never been addressed beyond preliminary studies. Fusion propulsion, if it could be made to work, offers the most plausible path to interstellar speeds. Fusing deuterium and helium-3, for example, releases energy with an efficiency roughly 100 times greater than fission. A fusion-powered spacecraft could theoretically reach 5 to 10% of light speed, with a fuel-mass ratio that is demanding but not physically absurd. The problem is that controlled fusion propulsion does not exist. Humanity has been working on controlled fusion power for over 70 years, and has yet to produce a sustained net energy gain in a terrestrial reactor, let alone a compact, reliable engine suitable for a spacecraft. The Bussard ramjet, conceived in 1960, proposed an elegant workaround. Instead of carrying fuel, the spacecraft would scoop hydrogen from the interstellar medium itself, funneling it into an onboard fusion reactor. The concept is seductive. If it worked, the spacecraft could accelerate continuously without ever running out of fuel, drawing sustenance from the very medium it travelled through. The physics demolishes this vision. At a typical interstellar density of 1 atom per cubic centimetre, collecting 1 gram of hydrogen per second requires a scoop with a frontal cross-section of tens of thousands of square kilometres. The engineering challenge of constructing and deploying a magnetic funnel of this scale is, to put it diplomatically, unsolved. Worse, detailed calculations performed in the decades following Bussard's original proposal revealed that the drag produced by interacting with even this extremely thin medium at relativistic speeds likely exceeds the thrust generated by fusing the collected hydrogen. The interstellar medium is too sparse to serve as fuel and too present to ignore as an obstacle. The ramjet becomes a brake. Even setting aside the propulsion problem, the journey itself presents hazards that compound over the immense timescales involved. Cosmic radiation pervades interstellar space at its full galactic intensity, the unshielded flux of the entire galaxy arriving from every direction simultaneously. Inside the heliosphere, the sun's magnetic field deflects a meaningful fraction of lower energy cosmic rays. Beyond the heliopause, that deflection disappears entirely. Any spacecraft or crew exposed to the unshielded interstellar cosmic ray flux faces a continuous radiation dose that accumulates relentlessly over the years and decades of transit. For biological organisms, this exposure is serious. Galactic cosmic rays include heavy ions, nuclei of elements like carbon, oxygen, silicon, and iron, accelerated to relativistic speeds. When these heavy ions pass through biological tissue, they deposit energy along dense, concentrated tracks that cause clustered DNA damage, far more severe than what lower mass particles produce. This type of damage is difficult for cellular repair mechanisms to fix correctly, leading to elevated rates of mutation, cancer, and degenerative tissue effects. Studies of radiation exposure in astronauts aboard the International Space Station, which orbits within the partial protection of Earth's magnetosphere, already show measurable biological effects from cosmic ray exposure over periods of months. Interstellar transit times measured in decades would magnify these effects enormously. Shielding helps, but cannot solve the problem at its root. The secondary cascades that a single cosmic ray triggers inside hull material mean that no practical thickness eliminates the threat. Better materials exist, and they reduce the dose measurably. But they do not eliminate it, and every kilogram of protective mass added to the spacecraft is a kilogram that must also be accelerated to interstellar velocities, compounding the already staggering energy requirements. Radiation protection and propulsion are locked in a zero-sum competition for mass budget, and the cosmic ray flux tips the balance against both. For electronic systems, the situation is somewhat more manageable but still significant. Radiation-hardened electronics can tolerate higher doses than biological tissue, but they are not immune. Over decades, cumulative radiation damage degrades semiconductor performance, increases error rates, and reduces the reliability of computational systems. A crewed interstellar vessel would require not just radiation-hardened primary systems, but redundant backups, and the ability to repair or replace damaged components over the lifetime of the mission, using only the materials and tools carried aboard. Now add the most psychologically devastating feature of interstellar travel: the absolute absence of any stopping point along the way. Within the solar system, destinations are distributed at intervals that, while vast by human standards, are at least conceivable. Mars is a few months away, Jupiter a few years. Even the outer planets are reachable within a human lifetime using current technology. Along the way, there are objects to study, gravitational assists to exploit, and at least the theoretical possibility of emergency diversions. The solar system is sparse by terrestrial standards but populated by galactic ones. Interstellar space offers nothing comparable. Between our solar system and the Alpha Centauri system, there are no planets, no asteroids, no comets, no stations, no objects of any kind that could serve as a waypoint, a refuge, or a resource depot. The Oort cloud, if it exists as theorized, may extend outward from our sun for a light year or perhaps two. Objects within it are icy bodies, small and widely scattered, gravitationally bound to our star. They are not clustered conveniently along departure trajectories. They are distributed across an enormous spherical shell with typical separations of billions of miles between individual objects. Even if a departing spacecraft happened to pass near an Oort cloud body, the encounter would be fleeting and the object itself would offer little of practical value, a dirty snowball a few kilometers across tumbling through the darkness. Beyond the Oort cloud lies the true desert. The space between our sun's outermost gravitational hangers-on and the equivalent boundary of the Alpha Centauri system is a region that current astrophysical models predict contains no solid body of any meaningful size. No rogue planets have been confirmed in this specific gap, though statistically some may drift through interstellar space in the broader galactic neighbourhood. No asteroids, no comets unbound from any star, no debris of any kind that a traveller could count on finding along the route. The interstellar medium itself, at 1 atom per cubic centimetre, provides nothing to work with. For a stretch of approximately 2 to 3 light years, depending on how far each star's Oort cloud extends, the journey passes through a region that is, as far as we know, entirely featureless. Try to imagine what this featurelessness would look like from inside a spacecraft. In the early months of the journey, the sun would still be the brightest object in the sky behind you, gradually dimming but recognizable. Alpha Centauri would brighten slowly ahead, but perceptibly only over years. Between those two reference points, the star field would remain essentially static. No object would approach. No object would recede at a rate visible to the human eye. No landmark of any kind would break the monotony. A crew member looking out a viewport on day 100 of the journey would see the same stars in the same positions as on day 1000. The visual environment would be indistinguishable from a high-resolution photograph taped over the window. Nothing moves, nothing changes, nothing happens. This sensory deprivation would persist for years. Even at 10% of light speed, the most optimistic plausible cruise velocity, the crossing to Alpha Centauri takes over 4 decades. For the vast majority of that time, the surrounding environment provides zero visual feedback of progress. Human brains are wired to interpret stillness as stagnation. Our sense of journey depends on changing scenery, passing landmarks, the feeling of covering ground. Interstellar space provides none of these cues. A crew that has been travelling for 10 years at blistering speed would look out the window and see a sky that appears identical to the sky they saw when they departed. The psychological toll of this unrelenting sameness, sustained over decades in a confined vessel with no option for shore leave, no possibility of turning back, and no guarantee that the destination will prove hospitable, is a challenge that no human expedition has ever confronted at anything remotely approaching this scale. No stopping points also means no resupply. Every molecule of water, every kilogram of food, every replacement component, every calorie of energy required for the entire voyage must be aboard the vessel when it departs. There is no option to refuel, restock, or repair using external resources. A malfunction in deep interstellar space cannot be addressed by a rescue mission. The nearest help is light years behind you and light years ahead. The concept of emergency, which in every other context of human experience implies the possibility of rescue, or at least retreat, becomes meaningless in interstellar space. There is no rescue, there is no retreat. There is only forward, into more of the same emptiness, for years or decades, with whatever you brought with you and nothing else. The communication situation compounds the isolation in ways that evolve cruelly over the course of a voyage. At launch, a spacecraft departing the solar system would maintain near real-time communication with Earth. Delays would be measured in hours, comparable to current deep space missions. Conversations would be slow but functional. Mission controllers could respond to questions, provide guidance, upload software patches, and offer the psychological comfort of a connected link to home. But the delay grows with distance, and it grows at the speed of light, which is the fastest any signal can travel. At 1/10 of a light year from Earth, roughly the distance at which the sun's Oort cloud might begin to thin out, the one-way communication delay would be approximately 37 days. A question sent to Earth would receive a response more than 2 months later. Already, conversation has degraded to correspondence. Mission Control can still offer advice, but it arrives too late to help with any time-sensitive decision. At 1 light year, the delay reaches 1 year in each direction, a 2-year round trip for a single exchange. At this distance, Communication with Earth resembles the exchange of letters between continents in the 18th century, except each letter takes a year to arrive rather than months. The emotional connection to home weakens. The crew knows that the people they are communicating with have aged a year between question and answer. Events on Earth that were current when the message was sent are ancient history by the time the reply arrives. At 2 light-years, the midpoint of a crossing to Alpha Centauri, the round-trip delay exceeds 4 years. A child born on Earth when a message was sent would be starting school by the time the reply reached the spacecraft. The conversation has not merely slowed, it has ceased to function as conversation in any meaningful sense. The crew could still transmit reports, Earth could still transmit encouragement, news, and cultural updates, but the exchanges would be monologues, each party speaking into a void and waiting years for an echo that arrives stripped of all immediacy and relevance. Signal strength deteriorates alongside delay. Radio transmissions weaken with the square of distance. A signal that is comfortably detectable at 1 astronomical unit becomes 10,000 times fainter at 100 astronomical units and billions of times fainter at interstellar distances. The Deep Space Network, NASA's array of massive radio dishes used to communicate with interplanetary probes, can maintain contact with spacecraft at the heliopause, only because the spacecraft carry relatively powerful transmitters and the ground stations use antennas up to 70 meters in diameter. At interstellar distances, even these systems would struggle. Maintaining a data link at 1 light-year would require either vastly more powerful transmitters aboard the spacecraft, consuming precious energy reserves, or vastly larger receiving arrays on Earth, spanning kilometers rather than meters. Communication does not become impossible at interstellar distances, but it becomes expensive, slow, and functionally one-directional over the timescales relevant to a voyage. By the final years of a crossing, a crew would exist in a state of communicative isolation unprecedented in human experience. Messages from Earth would arrive years after they were sent, carrying news of a world that has moved on without them. Replies sent from the spacecraft would not reach Earth until years after the voyage had ended, one way or another. The crew would, for all practical purposes, be alone. Not alone in the romantic sense of an explorer on a remote mountain. Alone in the absolute sense of being the only conscious beings within light years in any direction, separated from every other human by a gulf of space and time that no signal can bridge quickly enough to matter. All of these constraints, energy, radiation, isolation, sensory deprivation, communication decay, absence of resources, apply to the simplest possible interstellar crossing, a trip to the single nearest star. The distances to other stars escalate rapidly, and the compounding of every difficulty makes each additional light-year qualitatively more punishing than the last. Within 10 light-years of the Sun, there are approximately 12 known star systems. Some are single stars, others are binary or triple systems. The average spacing in this immediate neighbourhood is a few light-years, which is relatively dense by galactic standards, because we happen to sit within a moderately populated region of the Orion Spur, a minor structural feature between larger spiral arms. But even within this relatively cosy neighbourhood, the difficulty of reaching specific targets varies enormously. Alpha Centauri at 4.24 light-years is the closest. Barnard's star at 5.96 light-years is the next nearest single star. Wolf, 359, at 7.86 light-years. Lalande, 2.1185 at 8.31. Sirius at 8.6. Each additional light-year of distance does not simply add a proportional amount of travel time. It compounds every challenge simultaneously. A voyage to Barnard's star at 10% of light speed would take roughly 60 years instead of 42. Those extra 18 years demand 18 additional years of food, water, air, and energy. 18 more years of cosmic ray exposure. 18 more years of material degradation, mechanical wear, and electronic fatigue. 18 more years of psychological endurance in a confined, unchanging environment. 18 more years during which any single point failure in a critical system could prove fatal with no possibility of external assistance. At 10 light-years, the pool of accessible stars expands modestly, but the transit times stretch to a century, 100 years aboard a spacecraft. No human being has ever lived that long, let alone lived that long inside a metal vessel hurtling through a radiation-saturated vacuum. A journey of this duration would require either technologies that do not currently exist, such as reliable suspended animation, or a fundamental reconception of the mission as a generational endeavour, a vessel designed not for a crew that departs and arrives, but for a population that lives and dies aboard the ship, with their descendants completing the voyage. Generational ships introduce their own cascade of difficulties. Maintaining a stable, functional society for a century or more within a closed environment with finite resources and zero external input is a social engineering challenge without precedent. Every calorie must be produced on board through agriculture or recycling. Every berth must be balanced against available resources. Every dispute must be resolved without the option of anyone leaving. The ship becomes a world unto itself, a sealed terrarium that must sustain human civilization across multiple generations while travelling through a void that offers no help and no forgiveness for mistakes. At 20 light-years, the transit time at 10% of light speed reaches 2 centuries. At 50 light-years, 5 centuries. At 100 light-years, a millennium. These are not distances to obscure stars in remote corners of the galaxy. These are distances to the nearest few thousand stellar neighbours in our own arm of the Milky Way. The galaxy itself spans 100,000 light-years. At 10% of the speed of light, crossing it would take 1 million years. Even at the speed of light, a physical impossibility for any massive object, the crossing would require 100,000 years, a span roughly equal to the entire existence of anatomically modern humans on Earth. Each step outward along this ladder of distance deepens the isolation and multiplies the hostility. A ship travelling to a star 50 light-years away would spend 5 centuries in the interstellar medium, 500 years of cosmic ray bombardment, 500 years of equipment aging, 500 years of recycling the same water, the same air, the same finite stock of materials, 500 years during which a message sent home would not receive a reply for a century. The crew that departed would be ancestors, mythological figures to the descendants who eventually arrived, if anyone arrived at all. And the character of the medium through which the ship travels never changes. It is the same 1 atom per cubic centimetre at 50 light-years as it is at 4, the same cosmic ray flux, the same magnetic field, the same absence of shelter, landmarks, and resources. The interstellar medium does not become more hospitable at greater distances. It does not offer oases or rest stops or regions of enhanced density where a traveller might pause and gather strength. It is uniform in its barrenness across spans of space that encompass millions of potentially habitable worlds, each one separated from its neighbours by this same implacable desert. The galaxy is large enough that interstellar space transforms from a challenge into a cage. The distances are not merely inconvenient, they are isolating in a structural sense. Each star system exists within its own tiny sphere of warmth, energy, and protection, surrounded on all sides by a medium that offers nothing to anything attempting to bridge the gap. The gaps are not just wide, they are empty, and the combination of width and emptiness creates a barrier that is qualitatively different from any obstacle that speed or cleverness can straightforwardly overcome. This is the nature of the hostile desert that fills the galaxy between its stars. It has no defences because it needs none. Its weapon is not force but absence, the slow accumulation of nothing over distances so vast that time itself becomes the enemy. Light year after light year, it offers no sustenance, no reprieve, no change in conditions, only the steady compounding of distance, radiation, and deprivation over spans of time that mock human lifetimes, human engineering and human patience. The medium itself is thin, the distances are not, and it is the distances, amplified by the barrenness of the medium, that transform interstellar space from an empty corridor into something far more formidable, a barrier that may define the fundamental character of the galaxy itself. What remains to be understood is the most unsettling realization of all. This barrier is not an anomaly within the Milky Way. It is not a localized desert between a few unfortunate stars. It is the dominant physical feature of the entire galaxy, and what it reveals about the true nature of our cosmic home challenges everything we think we see when we look up at the night sky. Step back now from the spacecraft and the engineering and the calculations of energy and velocity. Forget for a moment the question of whether humans could ever cross the interstellar void. Set aside the radiation dosimetry and the fuel mass ratios and the travel times measured in millennia. Instead, ask something more fundamental, something that does not depend on technology or ambition or cleverness. Ask what the Milky Way actually is, physically. when measured not by its luminous highlights but by its total volume? The answer to this question is the most important thing in this entire story, because it reveals that interstellar space is not an unfortunate obstacle between the interesting parts of the galaxy. It is the galaxy. The stars are decoration. The void is the substance. And understanding this inversion, truly absorbing what it means, changes the way every photograph of the night sky should look to you forever. Begin with the dimensions. The Milky Way's disk spans roughly 100,000 light-years in diameter and averages approximately 2,000 light-years in thickness. This disk is where the majority of stars, gas and dust concentrate, the visible architecture of spiral arms and dense stellar neighborhoods that fills the images in every astronomy textbook. Above and below the disk extends the galactic halo, a diffuse spherical region populated by ancient globular clusters, scattered individual stars and an enormous envelope of dark matter. The halo extends outward to at least 130,000 light-years from the galactic center, possibly much farther depending on how the boundary is defined. Even confining the analysis to the disk alone and ignoring the halo, the total volume is staggering. A cylinder, 100,000 light-years across and 2,000 light-years thick, contains roughly 15 billion cubic light-years of space. The halo adds substantially more. Including, it brings the total galactic volume to something in the range of several trillion cubic light-years, though the precise figure depends on where you draw the outer boundary of a structure that fades gradually rather than ending sharply. Now consider how much of that volume is occupied by stars. Our Sun is a fairly typical star with a diameter of roughly 860,000 miles. Converting to light-year units, that diameter is approximately 0.00000015 light-years. Even the largest known supergiants, bloated red stars like UY Scuti or Stephenson 218, measure only a few billion miles across, still a negligible fraction of a light-year. Stars are extraordinarily small relative to the spaces that separate them. In the solar neighborhood, the average distance between adjacent stars is roughly 4 to 5 light-years. Each star occupies, on average, a private volume of approximately 7 to 8 cubic light-years. Within that volume, the star itself, even a generous estimate of its physical size, fills a fraction so small that expressing it requires scientific notation. The ratio of a typical star's volume to the volume of the space it occupies is on the order of 1 part in 10 to the 22nd power. Written out, that is a 1 preceded by a decimal point and 21 zeros. It is roughly the same ratio as a single marble compared to the volume of the entire Earth. Scale this across the entire galaxy, and the picture becomes overwhelming. If you could somehow sum up the volume of every star in the Milky Way, all 200 to 400 billion of them, the total stellar volume would occupy less than 1/1000th of 1% of the galaxy's total volume. The rest, the other 99.9999999%, is interstellar space. Gas at 1 atom per cubic centimetre, magnetic fields at a few microgauss, cosmic rays streaming silently in every direction, dust grains separated by distances larger than city blocks. The thin, hostile, functionally barren medium that this entire story has been describing. The galaxy is not a city of stars with gaps between them. It is an ocean of interstellar medium with stars scattered through it like grains of pollen drifting across a lake. The grains are real. The lake is what defines the environment. If you were to select a random point anywhere within the Milky Way's volume, the probability of that point falling inside a star, or even within an astronomical unit of a star, is so close to zero that for all practical purposes, it would never happen. The overwhelming likelihood is that your randomly chosen point would land in interstellar space, surrounded by near vacuum in every direction, with the nearest star a dim point of light several light years away. This statistical reality is obscured by the way humans observe the galaxy. When we look at the Milky Way stretching across the night sky, we see stars, thousands of them to the naked eye, billions through telescopes. The visual impression is one of abundance, even crowding. The galactic disk appears to overflow with luminous points packed shoulder to shoulder in a glowing band, but this impression is a projection artifact. We are collapsing a 3-dimensional structure thousands of light years deep into a 2-dimensional image on the inside of our retina. Stars that are separated by enormous gulfs of empty space appear to overlap when viewed along the line of sight through the disk. The apparent density is an illusion created by the geometry of observation. If you could somehow view the galaxy from outside, from a vantage point millions of light years away, and if your eyes could resolve individual stars, the truth would be immediately apparent. The spiral arms would appear as faintly luminous wisps against a background of almost absolute blackness. The gaps between individual stars would be visible as vast dark regions punctuated by isolated pinpoints of light. The overall impression would not be one of a dense, busy structure teeming with stellar activity. It would be one of overwhelming emptiness, interrupted by occasional, widely scattered sources of light. The galaxy would look sparse. It would look lonely. It would look like what it is, a structure defined not by its matter but by the void between its matter. This perspective applies not just to the Milky Way but to every spiral galaxy in the observable universe. Andromeda, with its trillion or more stars, follows the same mathematics. The vast majority of its volume is interstellar space. The Triangulum Galaxy, the Whirlpool Galaxy, every grand design spiral and every modest dwarf irregular, all of them are predominantly void by volume. Stars are everywhere outnumbered by the void surrounding them. Interstellar medium is everywhere the dominant reality. Within the Milky Way itself, the distribution of interstellar space is not uniform. The spiral arms are denser than the interarm regions. The galactic center is more crowded than the outer disk. The midplane of the disk concentrates more gas and dust than the regions above and below it. But even in the densest parts of the galaxy, interstellar space dominates. The central molecular zone near the galactic core, one of the most active star-forming regions in the Milky Way, still contains far more volume of interstellar medium than volume of stellar material. The spiral arms, those bright highways of star formation visible in images of external galaxies, are enhancements in density relative to the interarm regions, not solid structures filled with matter. A spiral arm increases the local stellar density by perhaps a factor of 2 or 3 compared to the interarm baseline. This is significant for star formation rates and for the visual appearance of the galaxy, but it does not change the fundamental character of the environment. Even inside a spiral arm, most of the volume is interstellar space. The interarm regions themselves are particularly stark. Between the Milky Way's major spiral arms stretch vast tracts of galactic disk, where the stellar density drops and the interstellar medium becomes even more dominant. A hypothetical observer positioned in the middle of an interarm gap, far from any spiral arm, would see fewer stars in every direction. The nearest stellar neighbour might be 10 or 15 light-years away rather than 4 or 5. The isolation would be deeper, the void more conspicuous, the sense of emptiness more acute. Yet even this enhanced emptiness would differ from the standard interstellar environment only in degree, not in kind. The interarm medium is still gas at roughly the same range of densities, still threaded with magnetic fields, still saturated with cosmic rays. It is simply more of the same, extending over larger, uninterrupted distances. Above and below the galactic plane, the situation becomes even more extreme. The disk is where most of the galaxy's gas, dust, and young stars concentrate. Rise a few thousand light-years above or below the midplane, and you enter the lower reaches of the galactic halo. Here the interstellar medium thins further, gas densities drop, dust becomes scarce. The stellar population consists primarily of ancient stars in globular clusters and scattered halo-filled stars, relics of the galaxy's earliest epochs. The spaces between these stars can be enormous, tens or hundreds of light-years of near-perfect vacuum separating one dim red sun from the next. The halo is interstellar space at its most absolute, a realm where matter is so rare that the concept of an environment, in any terrestrial sense, barely applies. What all of this means is that the hostility of interstellar space is not a localized hazard. It is not a danger zone that a traveller might someday learn to circumvent by finding a safer route through the galaxy. There is no safer route. The interstellar medium is everywhere. It fills the spiral arms and the interarm gaps. It extends above and below the disk. It occupies the halo. It stretches between every pair of neighbouring stars in the galaxy, without exception. There is no corridor through the Milky Way that avoids the thin gas, the cosmic rays, the magnetic fields, the functional vacuum, and the light-year distances. These conditions are not features of a particular region. They are the defining characteristics of the galaxy itself. This realization carries implications that extend well beyond the practical question of whether humans could ever build a starship. It speaks to the fundamental nature of the Milky Way as a physical structure, and to the relationship between the galaxy's luminous components and the vast, dark spaces that separate them. The stars that we see, that we study, that we name and catalogue and build stories around, represent the galaxy's rarest features. They are remarkable precisely because they are anomalies, brief concentrations of matter and energy against a backdrop of near-nothingness that stretches for light years in every direction. A star is what happens when a tiny fraction of the interstellar medium collapses under its own gravity and ignites. It is a temporary local violation of the prevailing emptiness, a pocket of extreme density and temperature embedded within a medium that is, by any human standard, empty and cold. When the star exhausts its fuel and dies, its material returns to the interstellar medium, dispersing back into the thin gas from which it came. The star was a momentary exception. The interstellar medium is the permanent state. Planets, moons, asteroids, comets, and everything else that orbits a star exist within the star's gravitational and, in many cases, magnetic domain. They are islands within islands, structures sheltered by the very anomaly that created them. Earth exists because a pocket of interstellar gas collapsed into the Sun and its surrounding disk 4.5 billion years ago. Everything we know, everything we have ever experienced, every ecosystem, every civilization, every individual life has unfolded on a tiny rocky body orbiting within the magnetic bubble of one star, itself a brief luminous interruption in the galaxy-spanning darkness. Beyond that bubble lies the interstellar medium, and beyond the neighbouring star's bubble lies more interstellar medium, and beyond the next star, and the next, and the next. More of the same, extending outward in every direction for 100,000 light-years, encompassing hundreds of billions of stellar oases separated by an ocean that offers nothing to anyone or anything attempting to cross it. This is the architecture of isolation. It is not designed, it is not intentional. It is simply the consequence of how matter distributes itself under the influence of gravity and thermodynamics in a universe governed by the physical laws we observe. Gravity pulls matter together into stars. Nuclear fusion converts that matter into energy for a few billion years. Then the matter disperses. Between the episodes of stellar concentration, the default state prevails. Thin gas, weak fields, cosmic rays, void. The galaxy is structured, at its most fundamental level, as a collection of isolated systems. Each star and its attendant planets exist within a tiny sphere of relative warmth and density, surrounded on all sides by an environment that is hostile not through malice but through absence. The barriers between these systems are not walls or shields or active defences. They are simply distance, multiplied by emptiness, compounded by time. And these barriers are not occasional features of the galactic landscape. They are the landscape. The stars are the exceptions. For any civilization, including our own, this architecture imposes a profound constraint. We can observe the galaxy. We can study its structure, catalogue its stars, analyse the spectra of its interstellar gas, and map its magnetic fields to extraordinary precision. We can know the galaxy in exquisite scientific detail, but knowing it and crossing it are different things entirely. The knowledge travels at the speed of light. A probe or a ship travels at a fraction of that speed, if it travels at all, through a medium that provides no assistance and exacts a continuous toll in radiation exposure, energy depletion, and material degradation over timescales that humble human patience. And here is the point that elevates this from a human engineering problem to something far more fundamental. The interstellar medium does not care how advanced the civilization attempting to cross it happens to be. A species 1 million years older than humanity, with technologies so sophisticated they might appear indistinguishable from magic to our eyes, would still face the same 1 atom per cubic centimetre, the same galactic cosmic ray flux streaming from every direction, the same absence of matter, energy and shelter between one star and the next. Technology can build faster ships. It can build better shielding. It can extend the duration over which biological or mechanical systems can function in hostile conditions, but it cannot change the medium itself. The interstellar gas does not become denser for a more advanced traveller. The cosmic rays do not politely diminish for a civilization that has mastered fusion or antimatter propulsion. The distances do not shrink, because the species attempting to cross them has been spacefaring for 100,000 generations. The medium is fixed. It is a property of the galaxy, set by the physics of gas dynamics, magnetic field generation, cosmic ray propagation, and gravitational structure formation operating over billions of years. No technology alters those underlying conditions. A starship can be designed to endure the medium more effectively, to cross it more quickly, to shield its occupants more thoroughly. But the crossing itself remains a passage through a region stripped of every resource, and the length of that passage remains measured in light years regardless of what powers the vessel. The barrier is not technological. It is geographical, in the deepest sense of that word. It is the shape of the galaxy, the structure of the space between stars, the physical fact that most of the Milky Way is made of something that is functionally nothing. This is what separates the interstellar problem from every other challenge in the history of exploration. The Atlantic Ocean was vast, but it contained fish, currents, wind, and islands. The Antarctic was brutal, but it had ice that could be melted and seals that could be eaten. Even the vacuum of interplanetary space offers solar energy in abundance and destinations distributed at intervals reachable within years. Interstellar space offers none of these mercies. It is a medium that cannot be harvested, cannot be used, cannot be modified, and cannot be shortened. It can only be endured. And it must be endured for years, decades, or centuries depending on the distance and the speed, with the full galactic cosmic ray flux bearing down on whatever dares to attempt the crossing. The medium does not adjust itself for ambition, it simply persists. The nearest star is 4.24 light-years away. The next nearest handful are scattered within 10 light-years. The nearest 100 stars are distributed within roughly 20 light-years. Beyond that, the numbers grow and the distances stretch, but the character of the medium never changes. It is always the same thin gas, the same magnetic fields, the same cosmic rays, the same absence of anything useful. A journey of 4 light-years and a journey of 4,000 light-years differ in duration but not in character. The interstellar medium is scale invariant in its hostility. It does not become easier or harder at different distances. It is simply more of the same, extending without interruption for as far as the galaxy reaches. This is why the terrifying truth about interstellar space is not reducible to a single dramatic fact. It is not that the temperature is extreme, although it is. It is not that the radiation is dangerous, although it is. It is not that the distances are vast, although they are. The terrifying truth is that all of these conditions combine to create a barrier that is not made of anything. It is made of nothing. The absence of matter, the absence of energy, the absence of shelter. The absence of any feature that could make the crossing less than a total commitment of resources and time, on a scale that may exceed what any physical system, biological or mechanical, can sustain. Emptiness is the barrier. Not a wall of stone or a field of energy, but the simple, patient, universe-spanning fact that between one star and the next there is almost nothing, and that almost nothing extends for trillions upon trillions of miles without a single interruption. The medium does not resist you. It does not fight you. It does not need to. It simply offers you nothing, and it keeps offering you nothing for years and decades and centuries, until either you arrive at the next island of warmth or you do not. When we look up at the night sky and see the stars, we are seeing the exceptions. The rare, beautiful, temporary exceptions to a rule that governs 99.9999999% of the galaxy. The rule is emptiness. The rule is the interstellar medium, thin and cold and saturated with radiation, stretching without relief between every point of light we can see. Those points of light are separated from each other by distances that transform their proximity from an invitation into a taunt. The stars are close enough to see. They are close enough to study. They are close enough to dream about. They are not close enough to reach, not easily, not quickly. Perhaps not at all within the constraints of physics as we currently understand it. And this is not a temporary condition. It is not an engineering problem waiting for a clever solution. It is a structural feature of the universe at the galactic scale. The Milky Way was built this way. Gravity assembled its stars from a medium that was already thin, already sparse, already stretched across distances that light itself requires years to traverse. The galaxy did not become empty between its stars. It started empty. The stars are the anomalies that formed within the emptiness, and the emptiness remains, as it has remained for billions of years, as it will remain for billions more, the dominant, permanent, unyielding feature of the galactic environment. There is something both humbling and clarifying about this recognition. Humbling because it reveals the true scale of our isolation. Earth is not merely a small planet in a large universe. It is a tiny pocket of warmth orbiting within the magnetic bubble of one star, surrounded on all sides by a medium that would strip away every protection and every resource we depend on for survival. The nearest alternative pocket of warmth is over 4 light-years away, across a gap that current technology cannot meaningfully bridge within human timescales. We are, in the most literal physical sense, alone on our island, able to see other islands in the distance but unable to reach them, clarifying because it puts the galaxy's beauty into its proper context. The Milky Way is magnificent. Its spiral arms are sweeping and elegant. Its star-forming regions blaze with the light of newborn suns. Its ancient globular clusters carry the memory of the galaxy's earliest epochs. All of this is real, and all of it inspires the awe that drives astronomy as a science and as a human endeavour. But the beauty is concentrated in the exceptions. The spaces between the beautiful things are vast and barren and silent, and those spaces are what the galaxy mostly is. We live in a galaxy of islands. Each island burns with nuclear fire, surrounded by a small family of worlds, wrapped in a bubble of magnetic protection, carrying within it the possibility of chemistry, complexity, and perhaps even life. But the sea between these islands is not water. It is vacuum. It is radiation. It is magnetic silence. It is distance measured in light-years and crossings measured in millennia. And that sea covers so much more of the galaxy than the islands do that to call the Milky Way a galaxy of stars is to mistake the decoration for the building. The Milky Way is a galaxy of emptiness. The stars are what make it beautiful. The emptiness is what makes it real. And somewhere tonight, 2 small spacecraft built by human hands drift through that emptiness, carrying golden records etched with the sounds of a world they will never return to, falling silently through a medium that does not know they are there, heading towards stars they will never reach.